Okay, so let us see. Yeah, thanks. Very hot, is it? Thanks. Good idea. Okay, so now we will be learning about the sine circle map. Okay. Yeah. So how the sine circle map looks like? How the sine circle map looks like? So remind yourself that we discussed this map, no? N plus 1 is theta n plus omega. And there is something mod 1. Hmm? Yes. Now we are looking into something, a new type of map, that is sine circle. Sine circle. So according to the map, you know that there should be a sine term somewhere. Okay, how can we incorporate this sine term? This is how. Yes. So instead of that, there are some derivations which I'm not going into, but this is the form. This is the form of that map. Okay, you can see what new addition we did. Okay, so theta n plus 1 is equal to theta n minus k by 2 by sine 2. Okay, so you can see that there is a sine term over here. And due to that, and there is a circle map also. So this is a sine circle map. Okay, now you can see now we have to totally depend on the computations. Okay, previously you were seeing that how it was omega and all. Now, due to that sine is a non-linear term, it is a bit difficult to predict. So you have to resort to the computer plotting. Okay. So previously, like this parameter is k. This is an important parameter. Okay. So this usually we take it greater than 0, like a positive parameter. K is greater than 0, and this parameter, how many parameter it has? It has parameter k. It has also parameter omega. Omega is also a parameter. So there are two parameters in this system. Okay, there are two parameters in this system. And you vary k and omega, and you are expecting to see lot of different diverse dynamical behaviors. Maybe it can be a fixed point, it can be a periodic point, it can be chaotic attractors. Okay, fine. So k, can you interpret? What if k equals to 0? What can you understand? What happens if k equal to 0? Yes, to 0. This sine circle map is reducing to the circle map. Okay, so when k equals to 0, the sine circle map transforms to the circle map, isn't it? Now, if k becomes non-zero, this transforms to a non-linear map, isn't it? Because why it is a non-linear map? Because of the presence of sine. Presence of sine function. Presence of the sine function. So k, can you understand that k is the measure of non-linearity? Non-linearity. That means if you see, if you put k equals to 0, it is reducing to a circle map. If k is non-zero, and if you keep on increasing k, it is increasing the magnitude of the sine. If it is increasing the magnitude of the sine, you can see the magnitude of non-linearity is increasing. You are putting lot of non-linearity into the map. For the idea, because k is multiplied here, k is multiplied with the sine. Agree? How many of you it is not clear? Agree with me or not? Okay. Why there is a 2 pi here? As usual, make the region between 0 to 1. Okay, to make the region between 0 to 1. So yeah. So omega is usually, so now we'll see what is this omega. Omega is usually the frequency known as the frequency ratio. Omega is usually the frequency ratio. Therefore, when it is rational, you say it is periodic. No. Then you say it is quasi-periodic. Okay. Fine with you. So far. Huh. So like that, scientists are developing new maps. Okay. That's how scientists are developing new maps. But I will feel that there will be almost topologically similar behavior as to this. Because both all are periodic. All are periodic. All are periodic with same 2 pi. Isn't it? Tan, how can you, what's the period of tan? Tan 45 is 1. Tan 0 is 1. Tan 0 is 0. Tan 90 is how much? Infinity. Yes. So no, I'm saying tan 0 is 0. Then when it is again 0, it is 0 at pi. Because sine pi by cos pi, sine pi is 0. So it is 0 at pi. Is there any other value before pi where it is 0? No, because sine has to be 0 and sine is 0 only at pi. So the period of tan is pi. Okay. So the period will be different. The period will be different. So accordingly, you have to divide by now pi, I think, due to the period or something like that. Okay. Or maybe 2 pi you can, because the full angle is 2 pi. The full rotation is 2 pi. But still, you will see almost the similar behavior. Okay. Functions. It would be a good exercise actually. It would be a good exercise. Like what happens if you consider different periodic functions instead of sine and all. Hmm? Okay. So this omega is the frequency ratio and K is known as the strength of non. You know, you got the intuition of why I am saying K is the strength of non-linearity. Okay. So when K equals to 0, remind yourself, when K is equal to 0, what happens? It's converging to the circle map, fine. Then what was the winding number omega? Correct. The winding number is just omega when K equals to 0. Fine. We proved it just before here. We proved it. For circle map, this is circle map. We just that the winding number omega is just equal to this omega. That is the parameter of your system. And this is when K equal to 0, right? This is when K circle map omega equals to omega. Yes. Now the question is, how can you find when it is K not equal to 0? What is it? It is bit tricky. It is bit tricky. Can you imagine computing Fn of theta naught minus theta naught by n? Just by analytical way? Can you do the second iterate? Can you do the second iterate of the map? It will be a bit hard. Okay. If you do the third iterate, it will be a bit hard. Okay. So I think Miss Shweta has done till 5. Is it? So you have to do it and it has to be done numerically. And if you do it only, then only you get some novel results which no one has got. Okay. That's the only way. Anyway, so how the function looks like. If you know before, if you remember yourself, previously, it was just linear, right? Previously, it was just linear. When you were considering this map, when you are considering the circle map, it was just theta n plus 1 is theta n plus omega mod 1. Okay. Now I'm, let's say the sine circle map. How can you say to me the form? I forgot. Theta n plus minus k over 2 pi sine theta n, is it? Sine 2 pi theta n mod 1. For this, it will be non-linear, surely, because of the sine function. Therefore, you see this non-linearity over here. But the logic is the same. The values keep on increasing, go till here, till 1. After 1, it cannot go more than 1. Okay, then again, the values will drop here. The values drop here. Okay, and you can see to some 0.4 and it happens like, okay. So you can see this is on the left, it is for 0.8. So 0.8. Now the moment maybe here, the moment you increase the value of k, that means you are saying I am adding more non-linearity to the map. Increasing k gives you more sign, more effect of sign, that is more non-linearity. That means the curve got even deeper. This is more non-linear now. More non-linear. Okay, k, and here k is equals to 2.0. Okay. So here this is, you are doing this theta n plus 1 versus theta n. This is known as a return map plot. This is, if you plot theta n plus 1 versus theta n plus 1 versus theta n, then this is known as the return map plot. Okay. Yeah. And what is omega here? Omega here is 0.5. But k is 0.8 here. So k is 0.8. When you increase k, what is happening to the plot? The plot syncs together. Something very interesting is happening here. Can you observe? Something very interesting is happening. Can you observe what is happening? Let us go back to the logistic map, the simplest case. Let us go back to the logistic map. What happens in the logistic map? What happens to the logistic map? So for the logistic map, what happens? You have the logistic map as Rxn into 1 minus xn. Okay. And if you plot xn plus 1 versus xn, you have this hump. But this hump tell you something more. This hump is not that just a mathematical function. It tells you more. What it tells you? Take any xn plus 1, take any xn plus 1, maybe this xn plus 1 here, suppose this you choose. Now you think from what xn this xn plus 1 came from. Oh, for a particular value of xn, then it goes to xn plus 1, no? I told in the previous class that it can be that two values of xn leads to the same xn plus 1. Isn't it? xn1, xn2 can lead to the same xn plus 1. Okay. Now can we see this happening? You took one value here, draw the straight line. Can you see that this is xn1, this is xn2? Both values of xn1 and xn2 are giving you the same xn plus 1. Mr. Jaydev got happy. I don't know what he saw. I think he achieved something which he did not achieve before. Okay. 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 Anyway, let us be back. So, game. You won lottery. Okay. Anyway, let us be back. So you know that's xn plus 1. Xn plus 1. What does this mean? This means this map is invertible. This property shows that logistic map is not invertible. Now the same question I would like to ask you here. Same question I would like to ask you here. Huh? What do you think? Is it invertible? Someone there. So if you see this case, yes, you see, no, yeah, it's okay. It is okay. It is not. But when you increase the value of capital K, this is a theta n plus 1, no? Fix this value, increase here. Can you see what is happening? You saw that you have these points on the x-axis. That means these points actually map to these points. Understood now? So three values of theta n, three values, that is theta n1, theta n2, theta n3. There are three such values of theta n1, n2, n3, which map to theta n plus 1. Agreed, right? So this is also non-invertible. So sine circle map is also non-invertible. But it depends on the parameter k. Depends on k. Because you see here, it did not happen. It did not happen. Okay. Only 1 point was there. But here you suddenly see that it is intersecting at 3 points. So depending on the value of capital K, the non-linearity measure, your map can be invertible and non-invertible. Okay. Fine. You can see, hence, we can say that this is something most important. Something most important here. Yes. Mr. Akulmari, come. Non-linearity strength is increasing. Okay. Can you agree to me that when suddenly, so what I ask you as an assignment, so these are the computational assignments. This is assignment. So assignment 1, I will check it in the afternoon. Assignment 1, computational assignment was for Hanon map. Oh, closed invariant curve. I already gave this last week. Sorry, the previous Monday. This was given on Monday, due today. Okay. Assignment 2 given today, due November 1st week, is plot the function, plot theta n plus 1, theta n, and confirm numerically that for k greater than 1, sine circle map is non-invertible. So these are the computational assignments. Okay, so be back. Okay, okay with you? So you just have to plot this like 8, but you saw the map was invertible, but suddenly the k was made to be 2, and you see it is non-invertible. But he is claiming something else. The book is claiming that we say that last line for k greater than 1. For k greater than 1, the map is non-invertible. I want you to show it by doing for different values of k, and take k equal to 1, take k equal to 0.95, 1.1, small, nearby 1, and convince yourself that how the invertibility changes. You will see for k less than 1, it is invertible, but for k greater than 1, it is non-invertible. Saw this happening in these two graphs. Okay, fine. So k equals to 1 is the boundary. K equals to 1 is the boundary for such phenomena to happen. Okay. So for k greater than 1, some theta n plus 1 will have more than one possible precursor, that is theta n. That we saw. Like here it had 3 theta n values, theta n1, theta n2, theta n3, which map to theta n plus 1. Okay. So I'm teaching this from the book of Hilborn. I will share it. All these pages are from Hilborn book. So again you can think that due to this folding action, due to this non-invertible action, it was also present in Hanon map, isn't it? Hanon map was also non-invertible. Logistic map is also non-invertible. This map is it. The invertibility and non-invertibility depends on the value of k. For k less than 1, it is invertible. For k greater than 1, it is non-invertible. That's a computational assignment. But due to property, there is folding and stretching action. Folding and stretching. I showed you the Baker's map, isn't it? How the blue part and the red part, they were combining to each other. Folding, again combining, folding, combining, and they were mixing. So due to the non-invertibility property, why non-invertibility property is interesting? Is because if the map is non-invertible, then this paroda making process happens. The stretching and folding, kneading, that is the kneading process happens, and that actually leads to chaos. If a stretching and folding is there, you can be sure that the map is chaotic. It will give you chaotic behavior at some parameters. So therefore, for this one, I was not convinced, because for this one, if you see, the value you take, it is invertible. No folding, no stretching and folding action. No stretching and folding. Okay. So I gave you the question, can this map, circle map, show chaotic behavior? Okay. So all these questions, whatever is coming, I'm telling just now, please note it down. These are assignments and these will give you more clarity. So if you increase, like see this one, yeah. So k is 0.5, k is 0.5 and omega is 0. Plotted this cobweb diagram. Okay, this cobweb diagram. But before that, maybe we can discuss that. Yeah, let us discuss the fixed points of the circle, sine circle. Fixed points of sine circle. Can you help in that? Can you help in that? What are the fixed point of the sine circle? What was the sine circle map? Theta n plus 1 is theta n plus omega minus k over 2 pi sine 2 pi theta n mod 1, isn't it? For fixed points, what you do? Theta, you equate like theta star, both sides, right hand side and left side. That is, this is theta n plus 1 is f of theta n. Okay. And for fixed points, what you do? Theta star is f of theta star. Isn't it? For fixed point, theta star is f of theta star. So can we compute theta star? Theta star should be f of theta star is the right hand quantity, isn't it? This whole quantity. That is theta star plus omega minus k over 2 pi sine 2 pi theta. Okay. Don't worry about that mod 1. We can compute at the last. So can you tell me what should be the theta here? Cancels here. What will get? Omega equals to k over 2 pi sine, sorry, theta star here, 2 pi theta star. Then, so you will get 2 pi, sorry, omega by k equals to sine 2 pi theta star. Okay. So we see that, and you know that the sine value will be in between -1 and 1. The sine value will be in between -1 and 1. Okay. So suppose if is it true? If k is greater than 2 pi, has at least one fixed point. Happens if k is greater than 2 pi omega, what happens to 2 pi omega? It will be less than 1, which is a quantity because sine has to be less than 1. It cannot be greater than 1. So your quantity 2 pi by omega should be less than 1 from this. This implies. Okay. You got the idea? Got the idea? This is less than 1, no? So 2 pi by omega less than 1. Sine is always less than 1. Cannot be greater than 1. So 2 pi by omega less than 1. So that implies k has to be greater than 2 pi omega. And this is the condition has to be met for the map to have fixed points. If this condition is not met, the map cannot have fixed points. So the important result is what you understood from this. The important result is something is important. The important result is fixed points. The fixed points can occur for certain combinations. Certain combinations of k and omega. Got the idea? So the important result is the fixed points can only occur. Can the fixed? So my question is other way around. For the circle map. For the circle map, can there be fixed point for any value of k and omega? For the sine circle map, can there be a fixed point for any value of omega? Huh? What is your answer? Miss Gayatri, are you having lunch? So, yeah. What I'm asking is, in the sine circle map, for this, yeah, maybe Abhiram, yes. Can the sine circle map have fixed points for any value of k and omega? When it can have? Yeah, k has to be greater than 2 pi omega. Is it? If k is greater than 2 pi omega, the fixed points can occur. So therefore I wrote the fixed points occur only for certain combinations of k and omega. Okay? Such that k has to be greater than 2 pi omega. Has to be greater than 2 pi omega. So as usual, if there are fixed points, you can examine the stability of the fixed points. Is the fixed point stable or the fixed point is unstable? How you can do it? You have to compute the derivative, the modulus of the derivative, and put it less than 1. Isn't it? 1D map concepts. You remember? What should be the what is f theta here? Theta plus 1 is f of theta n. No. What is f of theta here? This side, the right hand side. Full right hand side. F of theta will be theta plus omega minus k over 2 pi sine 2 pi theta. Isn't it? Don't worry about that expression. Go with the flow. Go with the computation. That's it. So this is f of theta. For stability of fixed points, what we need? F prime theta star should be less than 1. Isn't it? Can you tell me what should be f prime theta? Theta is 1. You do a derivative with respect to theta, right? That is d by d theta of theta plus omega minus k over 2 pi sine 2 pi theta, right? Fine. Agree? What is d theta by d theta of theta? That is a linear. So it is 1. Okay. So it is 1. What should be this is omega is a constant. So the derivative will be 0. This is a constant. Take it outside. Derivative of sine is cos. Cos inside is 2 pi theta, then take the derivative of 2 pi theta, that is 2 pi. This 2 pi will be cancelling with this 2. So you will be having 1 minus k cos 2 pi theta, f prime of theta. Okay. So can you tell me what should be? So we need, what we need from this mod. So we need, what we need, mod of f prime of theta star should be less than 1. So mod of 1 minus k cos 2 pi theta less than 1. Can you find the, can you find the range? Theta star, sorry. Can you find the range? Let me know. Let me know the range you get after computation. What does this mean? This means that this guy, if mod A is less than 1, that means A should lie in between -1 and 1. Apply this concept here. Yeah. What do you think? Tell me the value. It should be just a very fast calculation. It should not be that. What you got? Are you getting 0 to 2 cos 2 pi theta star? No? 0 to 2. Okay, this is the condition. So this condition is condition of the fixed point. Stability condition for fixed point. What is the fixed point here? Theta star is the fixed point. We still did not compute theta star because you have to solve this equation for theta star. This equation for theta star. Okay. And since it's a sine value, it will have a lot of fixed points. A lot of fixed points. Okay, let us see the cobweb diagram. You know this is the cobweb diagram. Cobweb. For two different values, we are showing it. On the left, see the A part. Here you have how many fixed points you have on the A part? How many fixed points? What is the fixed point definition? If it crosses the diagonal line, it should be a fixed point. So how many fixed points? Hmm? Yeah. You don't know whether it is intersecting there. You don't know whether it is intersecting there. So one is here, one is here. Okay. So you can see, so suppose this is 1, this is fixed point 2. Which one is stable and which one is unstable? if you take a nearby initial condition here, it converges to this guy. So this guy is stable. Stable. But if you see an initial condition has been taken from this guy nearby the fixed point, then it is traveling away from the fixed point. Away from the fixed point. So this guy is unstable. You can see that here, this is for a different value. This for, you can see this plot here on the right, k is 0.5, omega is 0.95. On this example, if you start from here, this initial condition is going like this point again. So this fixed point is stable. But since you took nearby initial condition, this was a fixed point, it moved away, this guy is unstable. Got the idea? Just graphical approach. Okay. Got the idea. This is carrying over to the first case of 1D maps. And you already read very carefully the concept of 1D maps. So that's good. That's good. So I think we are near to very nice concepts already. Yeah. So this is nothing but some simulations from the book. Okay, I urge you that if you want to know more about the behavior, try to do the bifurcation diagrams, cobwebs. It will give you more insights. Okay. Then one question is how periodic orbits look like. How periodic orbits in sine circle map looks like. So you can see this guy is a periodic orbit. Moreover, this is a periodic orbit of like 1:2. The ratio is 1:2 ratio. Okay. Can you understand why it is 1:2? Why it is 1:2? About why it is 1:2? See it happening. You can see it happen. I explained a lot of cobwebs just Monday, no? I took how it is iterating, and based on that you can do. For this, think about this. Don't consider this guy. Because this is the initial condition which is going like this. Okay. Is it okay? Think about this. Why it is 1:2? Why it is 1:2? We can take another example. I think these plots are not that clear for you because here they are not discarding transients. But I think I discussed last class these maps. Okay, last class I showed you these maps, and I told you how we could compute the rotation number in these cases. Okay, I think we saw this example, like how many intersections it is making with the function curve, 21 iterations, and for 21 iteration it does so by only moving once through the cobweb. So it is 1/21. How many times it moves, put on the denominator. How many point it intersects, put on the denominator. That is the rotation number. But can it be 2/21? Can it be 2/13? Something like that? Yes, it can be. So I think we have an example also. Maybe, yeah, this was a good example. This was a good example, like maybe here. Yes. So the pink one is doing 2 iterations, 1 iteration here, 1 iteration here. And so the number of iteration will be put on the denominator, that is 2. 2 times, like it went like this, then did something, and again came like this. So it came 2 times the cobweb. It went like this and again came like this, 2 times. And how many times it intersected? 27 times. 27 times. So therefore, you can see why the rotation number is now 2 by 27. So never think that always it will be 1 by something. It can be 2 by that, it can be 3 by that, it can get complicated. Yeah. Here this is a good example. Here you can see and you can count the number of things like periods. But it gets difficult increases. When the period increases, it is very difficult to count these numbers. What are the numbers? Okay. So I was thinking if some algorithm can be made which can think of this rotation number automatically. So these are the, and you know that they arrange, periodic orbits arrange themselves in some way. There is a pattern to it. Okay. It's just an example. You don't need to worry. Okay. How they organize sometimes in space, not randomly. Suppose you see a period 17 orbit and you see a period 18 orbit. Okay. Then you will surprisingly see the sum of those two another periodic orbit. That is 17 plus 18. That is 35. You see a period 35 orbit. That is being born from period 17 and period 18. Okay. 35. Okay. Maybe I did it in my notebook in a better way. Yeah. Yes. 17 and 18 is there. 35 is there. Okay. Now you take 17 and 35. What is the sum? 52. 52 is also there. Okay. Now you take 52 and 17. What is that? 69. 69 is also there. Okay. So this is a very cobweb like, very web like structure. Like, and this is something very nice. This is known as fairy tree sequence. Okay. Fairy tree sequence. Don't worry about the notation. It is a bit different. That means what you learned from this, 17 and 18, there can be periodic orbits of large periods. In between 17 and 18, how many periodic orbits you had? The sum of those two, 35, higher periodic orbit. 52, even higher, 53, 69, 71, 86, 87, 88, 89. Interestingly see why the difference between them is having a pattern. Here you see difference is 1. 86, 87, 88, 89. Here you see the difference is 2. 6, 71. Here you see the difference is again 1. So all these periodic orbits you are seeing in a nonlinear map, in a nonlinear complex map, has this. So that is quite remarkable, isn't it? Like in a nonlinear map, which you cannot even think analytically, computationally you do the calculations and you found a pattern. So Fairy found it in late 90s. So you can see at that time there was not such an advent of computers and all, but he could find the periodic orbits follow this sequence. So that was quite interesting. And yeah. So I just gave you an idea. Of what is about. So actually, let me go back to this example. This is actually a plot of a DC-DC converter. Okay, this is a system of a DC-DC converter. DC-DC converter you can actually model with maps, discrete maps. Okay, the behavior, voltage, the period, the ramp voltage, the circuit equations, all this. And this is that map. E0 is the voltage, A is some offset variable, something like that. Depending on the electronics things, don't need to know. But those variables, when you change parallelly, you get this structure, color-coded plot. Okay, this is done in GNU plot. It's a free avenue to plot. If you have data, you can plot it like this. It looks something very nice, isn't it? So yeah, so it's very nice, and you plot it. And these are periodic orbits. All these are periodic orbits. All these tongs, these are known as tongs. Okay, these are tongs. And there is Arnold, a French mathematician, who saw these tongs, presence of these tongs, And he said that yes, these tongs will be in every dynamical system. Whatever dynamical system you take, Hanon map also you will see these kind of tongs. Do you remember where in yes or no? It is hiding. It is hiding. To do that, let us rub all this. Can you see that? Can you see that there is a tong here? These are the tongs. These are the tongs. Okay, I did not zoom it, but these are the tongs. So I think it is time, I think, to show something interesting. Like I think this was done by Shweta. She's also discussing more on the circle map. Okay. So what she did, you know that the sine circle map has two parameters, isn't it? K and omega. So what she did, she plotted K on y-axis, I think omega on x-axis. This omega, no? This omega on x-axis, and you can see the values are varying from -1 to +1, and the y-axis K is varying from 0 to 12. And you see this remarkable structures. See this remarkable structures. Okay, remarkable structures. So you can see that. Yeah, I should tell you what this color means. I think the black colors are the periodic orbits. So black color, anything you see black, they are the regions where periodic orbit exists. Okay. Anything you see colored, like colored means colored blue, maybe, that then it is chaotic, I think. Chaotic orbits. Okay, fine. So if you do this color arrangement, the scaling of colors, you are doing a scaling of colors. So you see this figure, okay? And you see these tongs. These are the tongs. Tongs. And you can see such a nice phenomenon here, remarkable phenomenon, like the tong repeating itself infinitely, isn't it? You see in between this tong and this tong, you stop at one, there is another tong here. Okay. In between this tong and this tong, there is a tong, another tong here. Okay. Yes, like a fractal. It's like a fractal pattern. Okay. And in between this and this, you see another one, there. But most important observation is if your periodic or less period. Can you tell me what was the period of this one? Fixed point. Fixed point, is it? I think this is just a fixed point. Then can you this one? Do you remember this one? Okay, we will see that. So what I meant to tell you that if the period is 1 or 2, the area of the tong increases. Okay, and as the period increases, the tong size decreases. Okay, that's the observation. So you can feel that this is a tiny tong, this is a tiny tong. That means it should be of higher period. It should be of higher period. Okay, the tong should be of higher period. That's why it is a tiny tong. This is a fixed point, therefore it is occupying a large area. Okay. What? And really interesting, like, yes, maybe, yeah, you can see what I meant by that fairy rule. What I meant by that fairy rule. Maybe this is 1, this is 3, or something, this can be 4. This can be again 1 plus 4, 5, 1 plus 5, 6. So like this, the period keeps on adding, and you're generating this fractal structure. And most importantly, it is present everywhere. More and more of the tong. You can see this is there, this is also there. So these are quite interesting. So yeah, and this just is a work she is doing with the collaborators in Brazil. Okay, I should. So more importantly, like this organization you just see, here, maybe. Oh, fine, this color coded plot, but you see something even more interesting. Okay, what is more interesting here? What is more interesting here? What you see out of the blue? So these are the curves. Can you see this red curve and black curve? Sorry, green curve. These curves. So these curves are something known as extreme curves, which is very a new phenomenon. Like since 1960s or 1970s, people are already familiar with this diagram. Arnold Toms. Okay, Arnold found this, and after that it got popularized. But people just showed this diagram. Not much analysis was being done. So then recently many researchers talked about how they are organized in space. This is such a non-linear map. It is showing chaotic behavior, such a complex dynamic phenomenon, but still it is having such a uniform structure, such a uniform and fractal-like structure. Why? Okay. So therefore, they thought of taking it to a next step. They started analyzing it. Okay. They started analyzing it. Okay. When they started analyzing it, they found these extreme curves. We will learn more about this in the afternoon class, 2 to 3, right? We have. Hmm? So we'll discuss more about it. So yeah, hang on there. Yes.